antiderivatives. That means we will learn what it is and how helpful it is to know how to deal with the antiderivatives. That means, let's see, I type a few scenarios, few situations that we may deal with the anti-differentiation. That means probably based on the name, you can realize that anti-differentiation, it's simply the inverse, the opposite process to differentiation. Okay, that's actually what it is. And as mentioned, we may be in the situation in our life that we will know the rate of change of some items, some things, and we will try to recover the original function. Okay, that means having, like, let's say this, having a velocity of the particle, we would like to know the position, like the position function, the distance or displacement, depends. Or let's say the engineers, we may have a rate of change, the rate of change of the water leaking from a tank, okay, and we would like to recover an amount of the water, okay? Or we may have a rate of change of the bacteria population, like increasing or decreasing, but we would like to know what is the amount of the bacteria. Okay? That means having a rate of change, of course, means having a derivative. We would like to compute the derivative. No. We would like to recover the original function. Okay, that means that this will be the derivative of what function, and we have to find this. And this process is called anti-differentiation, or, as I said, indefinite integration, indefinite integral. Okay, that means let's see what we will do. I have the definition. Probably it's really trivial, but that's how it is. A function f, the capital F, is called antiderivative of the small f on the interval I if derivative of the capital F will give me a function. Yeah, that's what I said. We will have something, and to differentiate this, we will get the original function. Okay. That means now let's start and let's try to derive a few formulas. That means let's take something like this: 1/3 x cubed. And do you think you can tell me what is the derivative of 1/3 x cubed? What's the derivative of 1/3 x cubed? Oh, I think you can. Can you type? I worked nicely with the coefficient. What's just the derivative. I'm not asking for the antiderivative. What is the derivative? Yeah, of course, thank you. X squared. Excellent. Thank you, that's what I was waiting. Okay, another function, 1/3 x cubed plus 1. What's the derivative of this? Oh, you can type yes, thank you. It's exactly the same. That means what we're doing at the moment, on my right-hand side, we simply have derivatives. Okay, another function, 1/3 x cubed minus 1. What is the derivative? Of course, the same. Thank you, Maria. Okay, that's mean you can see, probably I have a point. That's mean now, if I will take a function, 1/3 x cubed plus any constant, I will have the x squared. Okay, that's mean now let's look at this. Okay, if I have function x squared, I know that this is the derivative. That's the rate of change. That's what I was trying to explain. What is the antiderivative for x squared? What is the antiderivative for x squared? I'm just writing. It's one of the function f of x, and since plus c covers like all of the constant, we will actually say that this is the antiderivative, and we will call that this is the most general antiderivative, okay, of the function x squared. Because I can show you the graph of all of these antiderivatives, right? Let's see. Yeah, that we can see it's a family of the function. That means they behave exactly the same. They are just placed in different, like we're shifting them a little bit up, a little bit down, but the shape, the rate of change is exactly the same. Okay, that's because the derivative of them is x squared. That's mean, of course, they are antiderivatives. Well, because even if I will think about the slope of the tangent, will be exactly the same. The constant is not affecting the shape. Okay, let me come back for now. As we can see, this is like something which actually this, I'm kind of showing you a circle. This kind of circle, like from differentiating and then anti-differentiating, it's the fundamental theorem of calculus, which I will talk about this more specifically in chapter 4, but that's the whole circle. Having the derivative and then recovering an original function. Okay, that's, we know this process. We know we confident to differentiate. Now we have to be confident to get back to anti-differentiate. Okay, let's see. Let's find a few formulas, and you will help me, of course. Okay, that means this is just like almost the same thing. I will just name that my antiderivative, like if we would like to find, if we would like to anti-differentiate, we always have to put the constant c. And we will call that this is the most general antiderivative, okay? If we have the constant c. Because we may have any antiderivative, but adding the constant c will cover all of the cases. Okay. So now let's start with the first formula, of course, with the power function. That means again, I will ask you a question the way that you confident that we just cover everything, differentiation. Okay, what is the derivative of x? Yeah, get ready and get type. Of course, 1. Okay, 1. Oh, good. That's now what I can say. What is the antiderivative for 1? What's the antiderivative for 1? Of course, x. Yeah, right. That's this is fundamental theorem of calculus. Derivative, antiderivative. Great. Let's look at this. What is the derivative of x squared over 2? What's the derivative of x squared over 2? Just x. Excellent. What is the antiderivative for x? Of course, it's this, right? X squared. I know. If it's too much for you to type, but it's just x squared over 2. Yeah, the fundamental theorem of calculus. Okay, x cubed over 3, derivative is x squared. Antiderivative for this, of course, is my original function. And maybe one more, x to the power of 4 over 4, the derivative is x cubed. That's me. Hopefully now, because what we know how to do this way, yes? You know how to give me this answer, no problem. Yeah? Now, based on these numbers, we can probably figure out the pattern, the formula, because now I will ask you the other way. I will give you this function, and without seeing this, I will ask for the antiderivative. I will give you this, and I will ask for this. Okay, that means based on these powers, we can probably figure out the pattern. Okay, that means you can see if we have x to the power of, no, let's say the anti-differentiation way, x to the power of 1, the antiderivative is x to the power of 2 over 2. For x squared, the antiderivative is x cubed over 3. Okay, yes, exactly. Thank you, Alan. That means what we realize, if I have x to the power of n, what will be the antiderivative? You just type. We will have x to the power of 1 number more, and then we will divide by the same number. Excellent. Really good. That means this, and this is the formula for the anti-differentiation. Antiderivative. Of course, I can add the constant c to have the most general antiderivative. Also, please note, this formula works for any number, n. We can have any number, not even like the positive integers, because that's the power function, but we may have any number, but we can't have -1, because you can see denominator, -1 plus 1 will give me 0. I can't divide by 0. Okay, that's mean any number, but not -1. If I will ask you to anti-differentiate x to the -1, we don't know. We have to wait for Math 141. Then I will show you. I will tell you the secret. Okay, that's make sure that you not do it. Or the other way is, because that's the same form, right? Sometimes that's the same function. I think please remember, we can't really anti-differentiate at the moment. Yeah, we have to wait for calc 2. But any other exponents, fine, we may use this. Okay. Oh, did I type some notes? I always type some notes, but let me just put, because sometimes you making the mistake, okay? We can't differentiate. I can still write Math 141. Especially when you see function 1 over x later, you will kind of like differentiate, anti-differentiate. No. We not really allowed to, at the moment, anti-differentiate this function. Okay. That means the only tool that we have is this formula. Now, let's look at some trigonometric function, okay? Because what we have to do is simply have to like reverse, like look backwards. We know the derivative of sine of x. Oh, actually, let me see this. Cosine of x. Derivative of cosine of x, negative sine of x. Tangent of x, secant square, cotangent. Negative cosecant square, secant tangent, negative cosecant cotangent. Okay, and now I will ask for the antiderivative. That's me now. Can you tell me what's the antiderivative for cosine of x? Antiderivative for cosine is, of course, sine of x. Right. Now, what's the antiderivative for sine of x? Antiderivative for sine of x, let me move that, because I will not give you, most likely, I will not give you negative sine. I will give you positive sine of x. Okay, and we can see that antiderivative for sine of x is negative cosine. Okay, antiderivative for cosecant square of x, it's negative cotangent. Antiderivative for cosecant cotangent is negative. That's we can see. We have to remember to keep these negatives. They will be simply on the other side. And that's always a little bit of, yeah. Always think like twice before putting the answer for the antiderivatives, because we so confident with the differentiation, but make sure that you know the process backwards. Okay. That means this is also a reference page. We have to know all of the formulas, the one way and the other. That means, of course, they are antiderivatives. Antiderivative for right-hand side. Okay, and then I have a table. Yeah, it is in your textbook. That means what is important? Important is this formula for the anti-differentiation, x to the power of n. Oh yeah, don't look at this. That's Math 141. I mean 141. I mean, you can still see this, but we don't need this now. We have to know the trigonometric, and we don't have to know the inverse, Math 141. Okay, and the rest of them is the same. Of course, when we have the addition of two functions, we can simply find antiderivative for all of them. Constant will stay constant and just focus on the main function, and anti-differentiate, the same thing. And also, please note, we still don't know any formulas for the product or quotient or chain rule. Okay, that's chapter 4. Okay, but we know this one, the power form. Okay, let's try. Example 1. Oh, actually, I don't know why it's example 3, but this is example 1 for us. Okay, find all functions g such that derivative is given, which means we have to recover a function g, we have to find antiderivative, which is the original function. For sine x plus 2x to the power of 5 over square root of x over x. That means, first of all, what I will do, I will rewrite a little bit this part, because you can see it's the quotient, and I don't know any rules for now. That means I will divide this, which will give me x to the power of 4, and I will divide this. Square root of x over x, it will be x to the power of half, x to the power of 1. We're subtracting. Okay, I can keep this way. Okay, that means this is the other fraction. And now I have expanded form. I can take care of everything. That means recovering a function, of course, is the anti-differentiation. Antiderivative, I will write. Okay, I will copy 4. Now you can tell me, what is the antiderivative for sine of x? What's the antiderivative for sine? It's negative cosine. I will put that negative in front of the 4. Thank you, that's, yeah. Okay, now I will copy 2. Antiderivative for x to the power of 4 is just x to the power of 5 over 5. And x to the power of negative half, it will be positive half, but I can write, since it's a fraction, negative 4 cosine of x plus 2 over 5 x to the power of 5, and this will be positive half and positive half. Dividing by half means multiplying by reciprocal, by multiplying by 2, and positive half means the square root of x. Okay, correct? Because this will be 1/2, which is square root. And at the end, I will add a constant c. Remember, we have to add the constants. Okay? That means this example is showing you that you have to still get the expanded form. Please do not deal with any product, any quotient at the moment. No, we only know the trig formulas and the power formula. Okay. Oh, I did type the solution. It's okay. Okay, and as I said, the anti-differentiation, it's really helpful. And also, when you have an expression with the function and the derivatives, we will call this expression as a differential equations. Okay, that means the differential equations are the equations that involves the derivatives and the function. And now what we can do, we will always add a constant c, of course. But if we do have some extra information, extra condition, okay, we can find the exact antiderivative. Because do you remember that function x cubed was like shifted up and down? But if I will say that I want a function with like and I can maybe provide 1 point on the graph, then I have to get that exact value. I mean that exact function. That means with this extra condition, we can find this unique antiderivative. And let's see. Yeah, this is the common example. Find f if the derivative is given, x root x, and the value for 1 is 2. That means you can see I do have a point on my graph, which means I will be not adding a constant c at the end. I mean, I will have a specific one unique function. Okay, that means let's start. First of all, I will again rewrite this as a 1 because I see a product. I can't really deal with the product like separately. This will be function x to the power of 3/2. Okay, that means this is the derivative. To recover a function, I will anti-differentiate. Okay, and antiderivative. Okay, that means what is the formula? X to the power of one number more and divide by this number. And I can still put the constant c, but we have to compute this constant c. Let's check how we can do it. This will be 5/2 and 5/2. Oh, probably I typed the answer, but it's okay. I just, okay, I will flip this and I can keep it. Okay, now I know that if the y value is 2, then x is 1. Can you see? That means I'm substituting the given information. And I can copy this. This is 1 to the power of 5/2, which is always 1. Okay? And let's see what we will have. 2. 1 to the power of any number is 1. And then I can solve for the constant c. 2 minus that fraction, which is 1 and 3/5. And I can write 8/5. And now what I will do, where is my function? My function actually looks really good here. In order to give the final answer, I will copy this function, 2/5, x to the power of 5/2, and plus 8/5. And that's what I was saying, one unique function with the given constant, because this constant belongs to this function if we want this function to go through the point 1, 2. Okay, so that's the way to solve it. Okay, let's see. Probably I typed the answer. Okay, I will remove the typing. Okay, let's do this one. Find f if the second derivative is given. Okay. We have second derivative. In order to recover the first one, we will anti-differentiate, and then we have to anti-differentiate again. Okay. And we do have a special extra condition, which probably we will find one unique function. Okay, let's see. That means this is my second derivative, 12x squared plus 6x minus 4. Do you think you can give me the antiderivative for 12x squared? What's the antiderivative for 12x squared? 4x cubed, really good. And for 6x? Yes, that's good. You even simplify the fractions. And for 6x? 3x squared, really good. Look at this. And oh, for constant, I should maybe ask you, you okay with this one? The antiderivative for 4? Of course, keeping the negative, it's 4x, because derivative of 4x is 4. Nice and easy. And always the constant at the end, always. Now let's do the process again. Again, antiderivative for 4x cubed is x to the power of 4. For 3x squared is x cubed. For 4x is 2x squared. For the constant is a constant times x, and then another constant, because we did anti-differentiate twice. Okay, that means now what I'm doing now, I'm taking my function, final function, and if I substitute instead of 0, the value is 4. If I substitute instead of x1, instead of x0. If I substitute instead of x1, the value is also 1. That means, let's see. Substituting 0, we have 0, 0, 0, 0, d. d is 4. Great. Now, substituting 1. 1 plus 1 minus 2 plus cx, plus c times 1 plus c plus d is 1. That's why we do have kind of like a system of two equations. Of course, d is 4. When I substitute 4, oh, this is actually gone. Subtracting 4 from both sides, it is 3. I will remove my, okay. That means my one unique function, antiderivative, which of course is the original function, it's with the constant that we just calculated. That is actually c, and this is d. Okay, as we can see, we have to, when we have a specific values. Okay, another thing that I would like to show you is this. Okay, we remember when we have a position function, in order to find the velocity, we will differentiate. Simple. Having the velocity and differentiating again, we will get the acceleration. That means now we have to look backwards. Having the acceleration, okay, in order to recover a velocity, we will anti-differentiate. Okay, we will anti-differentiate. That means the velocity is the antiderivative for A, acceleration. Or having a velocity, if we would like to recover a function, we will also anti-differentiate. That means position function, S, is an antiderivative for V. Okay, that's it. We can play with this. Having some initial values, we can get the exact antiderivative. Okay, that means let's see this one. A particle moves in the straight line and has an acceleration given by 6t plus 4. Its initial velocity at 0 is -6 centimeters per second, and the initial displacement, the original function, at 0 is 9 centimeters. Find its position function at t, s at t. Okay, this is acceleration. I will anti-differentiate to get velocity. That's antiderivative. That's antiderivative for 4 and plus the constant c. I can anti-differentiate again. 3t squared is t cubed, 4t is 2t squared, c is ct, and plus the constant d. And now I can use the same, I can follow the same steps like I did for the previous problem. If I took the velocity equation and substitute 0, I will get a value of -6. If I will take the displacement and substitute 0, I will get 9. As we can see, 0, 0, c equals to -6, 0, 0, 0, d equals to 9. That's actually what, that was nice. But please note, because I can tell you, the common mistake on the test is when you have the initial values, you assuming right away that the corresponding constants, c and d, will have the same values. Not always. Of course, this is maybe not a good example because this works this way, but not always. Okay, that means do not, if you will see the options, do not pick the options with like the same values for the constant. Okay, that means actually I can show you a question. We will skip this one. Oh, no, we will skip this one. Don't worry for this question. That's too crazy. Okay, don't worry. It's good to practice, but nobody will ask you this on the test. Oh no. And the same this one. This one is nice and quick. The only problem is the units. That's okay. Don't worry for this. You know the process probably, because we have to change the units. No, too much. We'll skip this, skip this one, because this could be your, I mean quiz question, final exam question. Okay, let's see. A particle moves in the straight line and has the acceleration given by t plus cosine t. Find the position of a particle given that the velocity at 0 is -1 and the position function at 0 is 5. Okay? That's when you can see we will do whatever, like we will do some process, of course, and you can probably think, oh, the last constant will be 5, and the constant for the first anti-differentiation will be -1. That means, oh, actually, this one is -1t. Okay? And then you will say, but I don't think this is the correct answer. Okay? We have to be really, really careful. I know that they correspond, but we have to be careful. Okay, let me remove this. Let's just do the process. T plus cosine of t. Okay, the first anti-differentiation. What's the antiderivative for t? Can you tell me this? It's just, yeah, t squared, let me write, thank you, t squared over 2, and, oh, thank you, Maria, plus sine of t plus the constant c. Really good. Okay, let's actually do the same way. Oh, another anti-differentiation. This will be t cubed over 3 and over 2 over 6. Who can tell me this antiderivative? Antiderivative for sine of t. Negative cosine of t. Really good. Please remember from now on, like, please really think, yeah, like, take more seconds than even we think. Okay, antiderivative for constant is just constant times t and another constant. Okay. But we actually have velocity. That means I can substitute 0 to my velocity. And I can have my constant. Okay, this will be 0, and then sine at 0 plus the constant, and it's equal to -1. Sine at 0, of course, is 0, then the constant is -1. Okay, constant c. Constant c, that means shall I, no, let me work on this. This will be 1/6 t cubed, I'm just moving this, cosine of t and minus 1t, and we still have to work on d. Okay, now I know that if I substitute 0 to the s, to the position function, I will get 5. Let's see. Oh, the position function is here. Let's do it. 0 over 6, of course, 0, minus cosine at 0, and c is -1, but times 0 is still 0, plus d equals to 5. And now, can you see this? Cosine, what is cosine at 0? It's 1. That means we can, as soon as you will see the trigonometric function, we will know that this quantity 5 is affected. It's affected by something. Okay, plus d is 5. D is actually +6, because I have to think about this -1. Let me move closer because this looks weird. This is -1. Oh no, hang on. Oh no, it's 1. Okay, 1, but it's minus. Okay. I just thought that I messed up my unit circle. But Maria actually gave me the correct answer. Okay, it's 6. That means I will remove this and I will put 6. And now, can you tell me which answer is correct? Which answer is correct? -1 was actually good, but +6. Yes, thank you. That means, please remember, do not miss this nice question. Do not assume right away that the constant will correspond to the initial values. Okay, good. Okay, that means I believe I still have another question, but it's the same thing.